Hello and welcome to Video Notes 4.5, where we're going to talk about a different type of inference using a single proportion called the one proportion Z interval. So to start this unit, we have been talking only about hypothesis tests, where we're sort of wondering whether some established fact is true or not about when it comes to a related group or a subgroup of a population. So like if we have new batteries that we think last longer, testing that against the hypothesis of the old batteries, or if we're interested in the, there's a fact about all teenagers. We wonder, do the teenagers at Fremont High School have to do with the same thing, or are they different in some sort of way? So that's what we're trying to figure out with a hypothesis test. However, very often in our lives, we don't actually know the parameter of interest, P or mu, there are other things as well, for the full population. So running a hypothesis test becomes a little bit difficult because you don't have the established fact about the whole population. So instead, what we may only know is the statistic from a particular sample, P hat, X bar, and et cetera. So in this case, we must then infer what the parameter is for the whole population based on only our sample statistic. So this is a different way to do some inference here. So let's consider a situation here in which marine biologists are studying a type of coral called the sea fan, and its survival as global water pollution becomes a growing issue. A research team randomly selects sea fans from the Las Redes Reef in Mexico, and they found that 54 of the 104 sea fans that they sampled were infected with a disease that has been linked to water pollution. So the first thing we're going to do here is just calculate what is our sample proportion. Go ahead and pause and find that. So you should have gotten this. P hat is 54 over 104. That's approximately 0.519 of sea fans, about 52% of sea fans in this sample. Okay, next question. What are the chances that the true population proportion P is exactly the same as P hat is a 0.519? Hopefully you said that the chances there is 0. The chances that you grab a sample that is exactly the center of your population is effectively 0, because you're talking about grabbing a particular value out of an infinite number of values, Even if you're close, it's not exactly the same. So yeah, you don't grab a sample and go like, great, that's also my population's proportion. Instead, we have to do some more things because of, well, let's look at this next question. If we collected another sample of sea fans, would you expect the sample proportion to be exactly the same? Why or why not? Pause the video and think about that. All right, so hopefully you said something like this. No. So no, you wouldn't expect it. We have sampling variability, if you recall, and so that means as you pull sample to sample to sample, you would expect your measurement you're interested in to be different. In this case, the proportion of infected sea fans will vary from sample to sample, which adds sort of evidence to the answer to number 2 as to why we can be pretty certain that our population proportion will not be nabbed perfectly by any sample we collect. So what do we have to do here? Well, that brings us to the main topic of the day here. What we do is we give ourselves what I call wiggle room here. So we can calculate something called a margin of error. Probably not the first time you've ever heard that word. We can calculate a margin of error on both sides of our sample statistic that we believe includes the true population parameter. Okay, so in order to find this margin of error, we can use the standard error of proportions. We use that in lieu of knowing the true proportion of the population and thus the true standard deviation for the population. So This is not the first time you've heard the phrase standard error. If you recall, we talked about it during a t-test, because in a t-test, while we would like to know the standard deviation of the population, you often do not, and instead only know the standard deviation of your sample. Well, remember with proportions, standard deviation is based off of the p-value that you find. We do not have the p-value this go around. We have instead a p-hat. The goal of this whole thing we're doing right now is to try to estimate p, but all we have is p-hat. And since we're using the sample in order to do this, we call it standard error instead. So the standard error, if you recall, standard proportion, if you recall, I'm gonna look over here at the formula sheet. That's gonna be on the second page here. So standard proportion, or standard deviation of our proportion, if you recall, is this. We call it p times q over n square rooted there. But in this scenario, we're saying we don't know what p is. We're trying to estimate it. We only have a p-hat. Well, that's where this other column that we've been ignoring for a very long time here shows up. This column right here tells us exactly how we can find the standard error. Notice it is the exact same structure and the same idea as finding sigma, but in this case, we're using the sample data. So that is our formula there that we're going to write down now. So we got that the standard error we call S sub p hat, it's supposed to be a hat, is equivalent to p hat times q hat divided by n, all square rooted. And just to clarify for our future selves, p hat, that is our sample proportion. Q hat is 1 minus p hat, and n is our sample size. So yeah, you don't have to memorize this because it is on that formula sheet for you. What you do need to recognize is that you do not have p, instead you have p hat, so we call it standard error instead. Cool, so with that, along with the empirical rule, if you remember, that's the 68, 95, 99.7 rule, along with sort of our normal curve, breakdowns in the z-score table that we have. We can create something called a confidence interval. And the goal of the confidence interval is to try to capture the population's true proportion. That's the whole goal. So it's an interval and not just a value, okay? Most of the time when you see in the news and they tell you like 48% of people believe blah, blah, blah. And the fine print you'll see down at the bottom, it says plus or minus 3%. And that is sort of talking about their confidence interval. They say 48, but it could be as low as 3% lower, 45, or it could be as high as 51. Nobody knows for sure because you're just taking a sample. And you hope that your interval can do that. But it's all based off of what confidence level you are at. So we can talk about different percentages of confidence, and that has to do with sort of that empirical rule. When you say that you're 95% confident, you're sort of thinking about the idea of, well, I know that in the normal curve, we can capture 95% of the data between these two values. So there are 3 common ones we use, okay? There is the 90% confidence interval, 95, and 99. Those are the most common ones. You can see why we probably wouldn't want to go lower than 90. That's not very helpful. And going above 99, you start just getting into these little tails, and so you end up going a lot wider without getting a lot more confidence there. And these correspond with specific, what we call Z-star values. So we don't call them Z-scores because they're not from a hypothesis test, but instead it's, very semantic. We're not going to worry so much about that. So instead, we'll just sort of go through the values here. So a 90% confidence interval corresponds to a Z-star of 1.645. 95%, so we rounded this earlier. Remember, we talked about 2 standard deviations away from the mean being 95%. That was an estimate. It turns out the actual more specific one is 1.960. You can see that's very close to 2. And then lastly, 99% is 2.576. Now, if you ever forget these, okay, and you might not, you probably will just retain them as you go along. But let's say you're in the middle of the test, you're like 99%. Oh my gosh, what is it? What is it? What is it? There's some simple ways to do it. The one that you will know right now is that you can actually use your calculator. There's a function called invnorm that will help you figure out what it is. Why don't we go over and take a look at that right now? So let me show you how to find your Z-star values should you forget on a test or something like that. So to do it, we're going to use the inverse normal distribution. So the same place we usually go for our distributions, we're going to go here. So go ahead and hit that. And then it's the third option down, invnorm. And what it has for us here is the area that we're interested in and the mean and standard deviation. Since we're dealing with Z, these are standardized scores. So we want the mean and standard deviation to remain exactly as they are there, 0 and 1. The area is what we need to play with. So it might seem like right now I've set myself up for a 95% confidence interval. However, that is not the case. I'm gonna hit enter and we'll see what the Z-star value is and see what it matches with. 1.645 if we round to 3 decimal places. Which Z-star value does that match with? Look at your paper. So that's the 90% confidence interval. But hold on. It clearly said 95%. See if you can figure out why this, where we have the area of 0.95, corresponds actually with the 90% confidence interval. So here's a demonstration for what just happened there. So I just decided to draw out a normal curve using our empirical rule. I've marked some things here. Let's just focus on the one that says 95%. So remember when we think about these empirical rule ideas, we're thinking about the middle percentage. We say 95%, and we're talking about confidence intervals. It extends in both directions from a measure of center. So it is 95% centered around, I have drawn P hat is what our confidence intervals end up using. But that's sort of the idea here. And so when you're thinking about the 95%, it is a center sort of area. What your calculator shows to you is a left hand. So you're thinking 95%. You're thinking about like, oh, I want all this area right in here. That should be 95%, right? Or approximately 95%. But the inverse normal function in your calculator does the whole left tail. It also finds all this area for you. So when you said 95%, it didn't find the middle 95%. It found this 95% over here, which is why it ends up cutting it off a bit short from what you would expect there. So what you need to think about is what is the sort of left tail to it all for you. So in this case, if I wanted to figure out where does the middle 95% match up, well, that means that if the middle 95% is given there, then what's left over on these tails is an additional 5% left over. Split evenly between them, there's 2.5% over here, and there's 2.5% over here. So this right here is not the 95th percentile, that is the 97.5 percentile, actually right there. So that's actually what I should be substituting into the inverse normal curve, so that way I can find what is the Z-star score. So let's see what happens there. We're expecting 1.96. Let's see what happens when we do that. So instead of, for a 95% confidence interval, the right end of that would be at the 97.5 mark percentile there. Keep those means and standard deviations the same, press paste, press enter, 1.9599, 1.96 if we rounds there. That is what we were expecting there. Let's do it one more time for good measure and see if you can come up with, oops, wrong thing, come up with the 99% confidence interval. So if we're interested in a 99% confidence interval, then that right end of it will end up at what percentile? So it'll end up at 0.995. There'll be a 0.5% left off the ends because a 0.5% on each side would be 1% off in total, which leaves us a middle 99%. Let's check to make sure that that works. Press paste, 0.2576. 2.576. That is what we said the z-star value is. So there you go. If you ever forget, you got your calculator nearby, you can find your z-star values by doing this. All right, so let's summarize here. So if we're finding a confidence interval, the way we calculate it is as follows here. It is going to be, for this particular example, p hat plus or minus z-star times the standard error. That's the formula for a confidence interval in this case. So it's your center of your sample, so the proportion in your sample, and then you're going to add or subtract your margin of error. So this little part here is the margin of error. And there you have it. That is the formula for a confidence interval. Why don't we go ahead and move over to the backside and try some of these problems out. So the first example, we're just going to go ahead and stick with this whole idea of the C fans here. So it's the exact same setup. What we want to do is we're going to go through the different phases here: state, plan, do, and conclude. We're going to stick with that because it'll help us out. It'll ensure that you get the most credit possible on our class tests and the AP exam as well. So state. Usually this is where we put our hypotheses, sort of like, what are we testing out? What are we doing, basically? Well, in this case, there aren't any hypotheses. So instead, we're going to write a sentence about what we're doing. So what we're doing here is we want to estimate the true proportion of C fans that are infected. That's our goal here. So state what we want to do here. We're not testing hypotheses. We're instead wanting to try to capture the true proportion for all C fans that are infected. All right, on to the plan phase. Remember, we start usually the plan phase by naming what we're doing. We're going to do the exact same thing here. What we're doing right now is we are constructing a one proportion Z interval. We know it's Z because we're dealing with proportions. And then we usually check conditions. We still want to do that here. We are going to check conditions. And it's the exact same three conditions. So I have high confidence that you can actually figure these out on your own. So pause the video and write them down and then unpause to see how I check them. All right, so here are the conditions. Randomization, that's given already in the problem there, so we state it. Independence, we're gonna assume that 104 is less than 10% of all C fans. I'm gonna guess that there are thousands, maybe even millions of C fans that exist out there. And then normality, usually we do in P in Q, but this time around we don't have P, thus we don't have Q, so we're gonna use the P hat. And so in this case, there are 54 successes from our sample, which means there are 50 failures. Both of those are over 10, so we're good to go on planning. All right, next, do. Do is where we do our math. We're gonna do the math just as we've done before here. So we're gonna state some of the things that we know already. We calculated P hat earlier, 54 out of 104, which is about 0.519. And we're gonna establish what Z-star value we're gonna go with. It says up in the problem that we want to construct a 95% confidence interval. See if you remember what Z-star value that is. It is 1.960, almost 2. I believe if you use 2 on the test, they take off some points, but you don't get it all wrong. The other thing we need to do is calculate the standard error. So remember that is P hat times Q hat over N all square rooted. So in this case, we're going to go 0.519 times 0.481. That's 1 minus that p hat value, over 104 square root, which gets us about 0.049. If you want to pause and try it in your calculator, go ahead. Otherwise, I'm going to continue on here. So now we have all the information we need in order to construct this interval. So the 95% CI, everyone knows that to mean confidence interval, so you can use that. So the formula is p hat plus or minus z star times standard error. So let's plug those in. We got 0.519 plus or minus 1.960 times 0.049, which we can simplify to 0.519 plus or minus, that multiplication gets us 0.096. Oh, jumped around on me there. So you can leave your answer like that, or it is an interval. So in math, when we write intervals, we typically do it with this sort of interval notation. So we can also write it as actually doing the subtraction and addition. So if we subtract 0.096 from 0.519, we get a lower bound of 0.423. And then if we add that margin of error, we get 0.615. So either way is acceptable to write your answer. It just depends on sort of what you want to do. Now your calculator, when you do it on your calculator, will only give you the latter answer there as the interval. So keep in mind, that's not a point. We're getting out of this isn't algebra. That's not a point. That is an interval from this to this is what that's saying there. So I just mentioned that our calculator can do this for us. Why don't we go ahead and take a look how to do that? Let's now go ahead and see how our calculator can do some of that do step for us and calculate our confidence interval for us. So what we're going to do is we are going to go to Stat and go over to Tests, like we normally have been doing for our hypothesis tests. And we're going to go down. You can notice that as you move down, you start to see the word interval pop up. We don't want Z interval. We want instead to keep going until we get to right there. Letter A, 1 prop Z int. So you can arrow down like this. You can also use your alpha and press the math button. I think will do it for you to get the letter A as well. But I like to arrow just because I'm afraid I might mess up the alpha. I don't use alpha button very often. So press enter. And so what do we end up with here? Well, it asks us for X and N. Remember, X is the number of successes. So in this particular case, our CFANS is 54. N is our sample size, that's 104. And then it asks for our confidence level. It wants it as a decimal, so even though we're saying 95%, put it in as 0.95. Go ahead and hit calculate, and there it gives it to you. It gives you your interval. It gives it to 5 decimal places for this in this case. We only did 3, which is totally fine. It also gives you your p-hat, so you can check that. And it tells you what n is, once again, just so that way you have that information. And there you have it. That is how you find a 1 proportion Z interval. All right, so here are the conditions. Randomization, that's given already in the problem there, so we state it. Independence. We're going to assume that 104 is less than 10% of all CFANs. I'm going to guess that there are thousands, maybe even millions of CFANs that exist out there. And then normality. Usually we do in P in Q, but this time around we don't have P, thus we don't have Q, so we're going to use the p-hat. And so in this case, there are 54 successes from our sample, which means there are 50 failures. Both of those are over 10, so we're good to go on planning. All right, next, do. Do is where we do our math. We're going to do the math just as we've done before here. So we're going to state some of the things that we know already. We calculated p-hat earlier, 54 out of 104, which is about 0.519. And we're going to establish what z-star value we're going to go with. It says up in the problem that we want to construct a 95% confidence interval. See if you remember what z-star value that is. It is 1.960. Almost 2. I believe if you use 2 on the test, they take off some points, but you don't get it all wrong. The other thing we need to do is calculate the standard error. So remember that is p hat times q hat over n, all square rooted. So in this case, we're going to go 0.519 times 0.481. That's 1 minus that p hat value over 104 square root, which gets us about 0.049. If you want to pause and try it in your calculator, go ahead. Otherwise, I'm going to continue on here. So now we have all the information we need in order to construct this interval. So the 95% CI, everyone knows that to mean confidence interval, so you can use that. So the formula is p hat plus or minus z star times standard error. So let's plug those in. We got 0.519 plus or minus 1.960 times 0.049, which we can simplify to 0.519 plus or minus, that multiplication gets us 0.096. Oh, jumped around on me there. So you can leave your answer like that, or it is an interval. So in math, when we write intervals, we typically do it with this sort of interval notation. So we can also write it as actually doing the subtraction and addition. So if we subtract 0.096 from 0.519, we get a lower bound of 0.423. And then if we add that margin of error, we get 0.615. So either way is acceptable to write your answer. It just depends on sort of what you want to do. Now your calculator, when you do it on your calculator, will only give you the latter answer there as the interval. So keep in mind, that's not a point written out of this isn't algebra, that's not a point, that is an interval from this to this is what that's saying there. So I just mentioned that our calculator can do this for us. Why don't we go ahead and take a look how to do that? Excellent. Now let's finish it up. Let us conclude. So our conclusion, just like with hypothesis tests, we want to write what sort of we can conclude. The math, the numbers, what does it all mean? Drawing it back into context. So this is a great way to conclude things. So it's a very simple sentence frame that I like to use that starts out like this. We are 95% confident that. I start all of my conclusions like that. Whatever confidence level we were using, I start with, we are 95% confident that, 99%, 90%, whatever level we're using. That what? That's the true proportion of all C fans that are infected. So note that I'm bringing the context in here. So what was the whole point of doing this? The whole point was to try to capture the population's proportion, the true proportion for the whole population, all C fans. And I did it with just a sample. So my conclusion is not about my sample at all. My conclusion is about the population. And I'm bringing the context back in. And what does the interval tell me? Well, it tells me that I have some confidence that the true proportion that are infected is between 42.3% and 61.5%. And there you go. So you are percent confidence that the true proportion of context is between the two values you found in your do step. And that is a conclusion that will get you full credit every single time. Now, you might have a couple of questions about this. What do we mean when we say 95% confident? Like, what does it mean to be 95% confident? That's something we will work on in class. We'll talk about it. We'll do a little demonstration to try to solidify what does that mean to be at this particular confidence level. The other thing you might be wondering is like, so is the true proportion between these two numbers? And here's the thing is that you shouldn't really know. The whole point of doing this is because you don't know what the actual p-value is. So you have no way of knowing whether the actual p-value fell in between here. You might have gotten unlucky and got a sample that is far lower or higher, and thus maybe your interval did not capture it. But we don't know, okay? But we'll get into sort of why we're confident, okay, that maybe we did. All right. Now you're going to try one on your own, okay? Here, I'm not looking for you to do the state and plan phases at all. You don't need to check any conditions. What I want you to do is use your calculator to do the do phase entirely, okay? You don't even need to write down everything if you don't want to. Just jump to your calculator like I showed you above and do the whole do phase. But what I really want to see on the page here is an awesome conclusion. So read through the setup and then think about how you're going to use your calculator and then write down an excellent conclusion to this. We will see you in class.